Hey folks, today we want to talk about power. Power is measured in what? You've seen light bulbs with watts on them, but here's the problem. Power was work over time, where work was force times distance. Hey, in a circuit, what the heck is the force and the distance? Well, it's actually the force on the electrons and the distance. We're going to have to come up with a special version of power for electricity. And it would be really nice if it involved voltage and current and things, stuff that we've already talked about. So recall, as charges flow through a circuit device like a resistor, a light bulb is a great example of a resistor, they lose energy due to collisions with the atoms in the wire. They start out, Mitchell, with a higher voltage. They start out with a higher amount of energy per coulomb. So they might start out at 7 volts. For Josh, we'll do that. Put a line through the 7. Then they might lose some voltage. Let's suppose you measured this to be 4 volts. How many volts did we lose going through that resistor? Do the math in your head, please. Yeah. By the way, typically in a circuit, we only label the resistor. We don't label the 7. We don't label the 4. You'll find we're just interested in that 3. Well, if we lost voltage, that means we lost energy per coulomb. We lost energy. We did work. That energy is transformed into heat energy, and it varies as it's related to voltage drop because potential energy is QV. So let's see if we can derive an appropriate equation for electrical power. Power is work over time, but in this case, because we're losing energy, it's energy loss over time. Power is QV over T. Yeah. But I'm just going to target these. I'm going to group those two together. Who remembers from lesson 1? What's Q over T? And if you're not sure, keep reading in the brackets a couple of lines down and look smart. What's, huh? This gives us our equation for electrical power. It's the voltage times the current. Or I times V, but typically it's written VI. We call this Joule's law. Those are the two equations that you'll be flogging to death for the next few weeks. Ohm's law, V equals I times R, and Joule's law, power equals V over I. I said to you at the beginning of the lesson before I started recording, for Ohm's law, because it's V equals I times R, if you know any 2, you know 3. Actually, with Ohm's law and Joule's law, if you know any 2, you know all 4. If you know any 2 of power, current, resistance, and voltage, you can calculate the other 4, which really means we can solve any point in the circuit. This is the one that's on your formula sheet. There are 2 more versions of it. Remember, power equals energy. What did I write here? Energy. Oh, yeah. Power equals, I don't know what I wanted to write here. Energy drop per coulomb of charge. Sure. Voltage times current. You know what? For some reason, I'm repeating myself. Let's put it in the box right here. This is the rate at which you lose power in a resistor. This is the rate at which power is transformed into heat energy. Power equals VI. There, that's Joule's law. Ohm's law was V equals I times R. Travis, what does V equal? Wherever I see a V voltage, what can I replace it with? Say the same thing. V is the same as what? When I see a V, what can I write instead? That gives us another version. Power is also I times R. times I. Yes? Except instead of writing IRI, what's an easier way to write I times I? So here's another version. This one is not on your formula sheet. Gotta be honest, this is the one I use the most and I've ended up memorizing just because I've found when I'm solving circuits, most of the time I happen to know the current and the resistance at that location. But it's redundant. It's redundant. Travis? Yeah, but it's not ringing. Trav?
Well, it depends how you look at it.
Trav? If V equals I times R, get the I by itself. What does I equal?
V divided by R.
I is the same as what?
V divided by R.
Wherever I see an I, what can I write instead?
V divided by R.
So another version of this is going to be V divided by R. Except instead of writing V, what's a nicer way to write V? So Joule's law has three versions. The one in the box up above is the one on your formula sheet. Strangely, the one that I use the most is this one here. This one here I almost never use. I don't know why, but it just seems when I'm solving stuff, Manny, it's rare that I only know the resistance and the voltage. Usually if I know the resistance and the voltage, if I know V and R, it's so easy for me to find I, then I know it anyways. But both of these are redundant. Convenient, but redundant. Little technical comment, by the way. Finding the energy lost by charges, I should really use the work energy theorem. I should really say this. This is a different version of the work energy. I should really say work equals the change in potential plus the change in kinetic. Really?
What is the WNC? That's written there.
How much energy you're starting with plus work done by a non-closed system outside energy source is how much energy you'll end up with. This is actually a more flexible and universal work energy theorem. I find it a little more confusing, but it handles really weird stuff too.
Thank you.
But here's the thing. When we're talking about a circuit Vicus, we're going to talk about after you've turned it on. For a split, and I mean really split second, when you flick the switch on, the charges go from at rest to moving. So there is technically a change in kinetic energy, but that is such a short time. And once they're moving, they all go at a constant speed because they're locked in the circuit. Well, if you're going at a constant speed, what's your change in kinetic energy? 0, which is why I was able to use work equals QV and not worry about kinetic energy change. But this is also why technically flicking a switch off and on does use slightly more power than just leaving it on permanently. Okay. That's me being technical. Not on your test, you don't need to, but I always have to make sure if I'm teaching you wrong, letting you know why I'm teaching you wrong or why it's right if I am doing it that way. Let's apply this to circuits. My friend Kiowa, who wants to go into electronics or work for BC Hydro, here's some basics, okay? In almost any appliance, you'll know the wattage because the wattage is printed on the appliance. So here is a hair dryer. It's a 1400 watt hair dryer. You're plugging it into a 120 volt AC current. By the way, the symbol for AC current is a little wavy line like that. So the symbol for direct current source or direct voltage source is that there, where the long line is positive and the short line is negative. If you have alternating current, both sides are positive and negative. It alternates. And so we show that with a little wave like that. Okay? Kiowa, what's this question you want me to find?
Current.
You know what? Let's go back to our good old DFIC approach since this is new. What have they told you in this question, Kiowa, my friend?
Volts.
I agree. What's the voltage source? How big?
120.
Yep. Again, technically, I think coming out of your outlets, it's 113.4, but 120 is a nice number. We'll be close. What else have they told me?
Watts.
Oh, what is watts a measure of? What is measured in watt? Someone said it, yeah? No?
Joule.
Power. They've told me power. What's the, Kiowa, what's the power of this question?
1400.
I'm looking for an equation that has power, voltage, and resistance. Do I have, power, voltage, and current in it. Do I have one? Yeah, it's on the previous page. This is Joule's law. Kiowa, can you read to me Joule's law, please? It's in the box on the previous page.
P equals VI.
Can you get the I by itself? That's what I'm going to write down.
Divided by Q.
I equals what? Just read me what I'm going to write. And you can let him figure it out, because that's part. No, you're telling him what to do.
I haven't seen it. V divided by power.
Power divided by V, is it not? Yes? What's the power?
1400.
What's the voltage?
120.
How many amps will run through this house circuit?
You can do that in your head.
What do you get? 11.7?
11.7
11.7 what? What are the units for current? I already said it.
amps.
Amps. So you ready? Here's the first question. Your house circuits can only handle 15 amps. Could you run 2 blow dryers from this plug? Nope, it's going to blow the breaker. That easy. I mean, so if you're blowing a breaker, this is what's going on. Somehow, if you add up all the amperages that you're demanding from your circuit, you're asking for too much. And on most of the circuits in a standard house, 15 amps. The exceptions are the dryer circuit, probably a 30 amp wire and circuit, and your stoves, probably 30 amps. Probably. Yeah.
You ever seen those 45 amp ones?
Oh, they make bigger, but generally they don't install them in houses. Fire hazard. Oh, they make far bigger, because for factories and things, you want way more power. Yeah. Is that a hand up? Nope. Again, just to give you an idea of what's really big and what's really small, I have here mix and match the following appliances with their power ratings. So on the left, I have 1, 2, 3, 4, 5, 6, 7 appliances. On the right, I've got a bunch of wattages. We're going to see if we can figure out which one goes with which. Your hint is the more heat you move around, the more voltage is transformed into heat, the more power you're going to need. Looking at those appliances, which of those do you think moves the most amount of heat around? It's actually more than a hot water heater. See, a hot water heater doesn't need to move a lot of heat around it, because once you get it heated up, that stores a lot of heat, and you just got to add a bit of a trickle to keep it hot. But you don't have to keep heating it up very much.
Microwave.
One of these just requires an awful lot of heat nonstop while you're running it. Dryer needs a separate special plug. What's the standard wattage of a dryer? What's the biggest wattage from that list? Yep. Which of these do you think moves the next largest amount of heat around?
Microwave.
Computer? The one that Josh suggested. Hot water heater. Hot water heater probably has about that many watts. Which of these moves the least amount of heat around? Which of these can run off of a tiny battery for almost a year?
Clock.
Okay, those give off almost no heat. So clock probably has around 0.1 watts. Hey, which of these is an average light bulb? I'm going to assume all of you at this late stage in your lives, your parents let you replace light bulbs finally, yes? So 60 watts? Okay.
Anywhere near as much as-
Yeah.
After the incident.
So I got computer, microwave, and kitchen fan. Which of these doesn't generate much heat? Yeah, kitchen fan gets rid of heat, so it's going to have the lowest wattage remaining, which is what? Kitchen fan, about 150 watts.
What?
Okay. They don't. By the way, put your hand on the electric motor of a kitchen fan. You'll feel it's warm-ish. Even if you've been leaving it run for a few hours, it's warm-ish. Yeah. All right, we got 2 left. Hey, what's the wattage of a large microwave oven? Yeah, 1200. This is why, by the way, it always says on food packages, microwave oven times may vary. Because small wattage oven might have 800 watts, medium 1000, big one 1200. How many watts does a standard computer use?
800.
Now, we're getting more efficient at this as we're designing chips that can run at higher and higher temperatures and not have to be cooled. But yeah. Okay. Gives you a rough idea, Mitchell, of what's big and what's small. Okay? Will you ask us this on your test? I would have no problem doing something like giving you 4 appliances and saying which of these likely has the highest wattage. Really what I'd be saying is, hey, which of these is moving the most amount of heat around? And it'll be pretty obvious. Or which of these has the lowest wattage, and it would be which of these 4 appliances moves the least amount of heat around. It'll be pretty obvious. So we've talked about power. Let's talk about energy, but let's talk about electrical energy. Electrical energy. Well, power is work done by electricity over time. You know what? Instead of writing work done by electricity, you can cross out W and you can just put an E there for electrical energy, not electric field. How would I turn that into an equation for electric energy? How would I get the E by itself? Yeah. You want to know how much energy an appliance is using? It's the power of the appliance times how long you leave it on, which on a basic level means the longer you leave something on, the more energy you're wasting. Well, duh, but there's the physics. This gives you an answer in joules. A joule is so small that if we gave your parents their energy bill in joules, their energy bill would be in the hundreds of millions of joules. And they'd freak. Now, the dollars and cents would still be small, but they would like, what do you mean you left the TV on? Do you know that cost us 500 million joules? Which sounds like a lot, or is it? So once you move out of the house, once you sign a deal with BC Hydro, instead, they're going to use kilowatt hours as their unit for energy. What's kilowatt a measure of? Power. What's hours a measure of? It is still power over time, but it gives you energy in a much smaller magnitude, numbers you can wrap your brain around. 1 kilowatt hour is about 3.6 times 10 to the 6th joules. It's 1,000 watts times 3,600 seconds. Typical household uses about 1,000 to 3,000 kilowatt hours of energy in a month. Let's actually crunch some numbers. Let's use a 60-watt bulb, example 5. If a 60-watt bulb is left on all month, let's assume it's a 30-day month, 24 hours a day. How much energy will it use in joules? Ah! You needed that. I saw you dozing, Kohei.
It's actually really annoying when you're watching his YouTube videos and all of a sudden you're wearing headphones.
Hey, with headphones, it's great, I know. I get some great comments on some of my videos every so often. It's great. So, Vikas, what's this question asked me to find for part A? Read carefully. What's it asked me to find for part A? So that's the units. What's it asking me to find in part A? And I didn't say what's it asking me to find. I said, what is that asking me to find? The amount of, so what does this question ask me to find? Energy. Electric energy in circuits, well, that is power times time. Did they give me the power in watts? What? How much time? I know. It's still 60. How much time in example 5, part A? All month. Sorry?
In 30 days. 24
So it's going to be 30 days times 24 hours times 3,600 seconds per hour. How many joules of energy? This is one bulb. And you get answers that are so big. This is why BC Hydro doesn't bill you in joules. That's one bulb. Okay? So add that up for a whole household. You'd be getting bills where your energy use was in the, well, this is 155 million joules for one bulb. You'd be getting bills in the billions or even trillions of joules. And we don't deal well with those kinds of numbers. But let's write it down. 1.552. No, 3 5s, right? Times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And that's in joules. Vikas, what do they want me to do for part B?
B or is given in kilowatt hours.
Okay. So if I'm going to do a conversion, I always start out by writing down what they gave me. Kyle, you might remember this because you had me last year. I always wrote down what they gave me. And then I want joules to cancel. So where do I want joules to be in the next fraction? On the top or on the bottom? I want kilowatt hours. And apparently the conversion factor is 1 kilowatt hour equals 3.6 times 10 to the 6th. I got that from right there. So I'm going to take this number, this 1.555 times 2 times 10 to the 8th. Am I going to times it by 3.6 times 10 to the 6th or divide it? Divide it because it's in the bottom of a fraction. Divide by 3.6. And I get 43.2 kilowatt hours, a much nicer number for people to wrap their brains around. Yes? Because what does part C want me to find?
Find the cost of living.
Okay. What's the rate they gave me in part C?
The rate's 6 cents per kilowatt hour.
Ah. You know what? I think I'm going to take this number here, 43.2, and multiply it by 6 cents per, except I'll change the cents to dollars. In other words, I think I'm going to go 43.2 times 0.06. That'll tell me how much it cost to leave this light bulb on for an entire month. And we're going to run into a problem. It's kind of a nice problem, but it's still a problem. Leaving a bulb on for an entire month costs how much money? It's too cheap. I'll go $2.59, although they'd probably round up. We're so good right now at creating electricity, especially here in BC. Here in BC, how do we generate most of our electricity? Do we have coal-burning natural gas plants, coal-burning plants? No. Do we have nuclear power plants? How do we get our power? We got dams, which we built a bunch of them in the 1930s and 40s, 50s, and 60s. And it is a fairly clean form of power, although it certainly wreaked havoc with our salmon stocks. We didn't know that at the time when we built the dams. And it also flooded a lot of areas. Those trees now are slowly rotting. That carbon is being released back as a greenhouse gas back into the carbon cycle. We didn't know that when we designed all these. We don't want to build new dams, really. So why do I ask you, why do your parents say turn off the lights? Yeah, to save $2.59. Really, to save the environment, because, well, what do you folks think? 10 years from now, are we going to want to be using more electricity or less electricity? Pretty obviously more. We need to find better ways of creating electricity with the systems we have right now. Okay? Well, Clay, really, for $2.59, someone might say, oh, you know what? that's less than 10 cents a day, I'll just leave that bulb on 24/7 for safety, for security, or just because I like light. I mean, who knows? We don't have a good, if power was the same price as gasoline, there would be a way bigger incentive, the same way gasoline prices incentivize you to ride your bike to school or walk to school. There'd be a bigger incentive to shut stuff off. Sadly, we're too good at it. Efficiency. Efficiency, short lesson, we're done. Recall that efficiency is defined as the ratio of power output or energy output to power. Well, you know what? I wrote it this way. Efficiency is power out over power in, or okay, that's a new one. I think we'll pause the video control recording for a second. So, quickly rewriting, because we had a little crash there, I said efficiency was power out divided by power in, or it was energy out divided by energy in. Really, I told you, hey, look, it's the smaller number divided by the bigger number. Just make sure the units match. Divide watts by watts or joules by joules. Don't divide joules by watts. So let's put this all together. A 60-watt light bulb is connected to 120 volts AC alternating current. It produces 58 joules of light and heat every second. It's left on for 8 hours. Electricity costs 6 cents per kilowatt hour. Find, Clay, what does part A want me to find? Well, folks, clue in. I'm either going to use V equals I times R or power equals V times I. Those are the only two equations. I know V. Okay. Oh, I know power? Okay, so Clay, can you, I equals what equation?
60 over 1.
No, what equation? Give it algebraically first, please.
Power over V.
Which in this case is going to be?
60 over 120.
Which you can probably do in your head.
0.5.
Yep. Okay, this will have half an amp running through it. B. Clay, what does B want me to find?
Resistance.
This is why I said to you, you know what? If you know any two of power, current, voltage, and resistance, you can find the other two. So they gave us power and voltage drop. Let's find resistance.
120 over 0.5.
As an equation,
Oh.
what would I write first of all, please?
V over I.
In your head, what is 120 divided by 0.5? Dividing by half is the same as multiplying by 2.
240
240 what? What do I measure resistance in?
ohms.
Ohms. Hey, you guys know who the best electrical detective is? Sherlock Holmes? They only get worse. Jason, what does part C want me to find? Okay, so efficiency is going to be what you get out divided by what you put in, but the units have to match. Now, I notice this bulb is rated, what it's sucking in is 60 watts. How many watts are we getting out? Well, I got to be careful. It didn't tell me how many watts we're getting out. It told me how many, what we're getting out. Joules. But notice the energy that we're getting out is 58 joules every what? Per second. Wait a minute. What is 1 joule per second as a unit if I write it nicer. That's it. This is actually, they did actually give me the power out. It's just that instead of saying I'm getting 58 watts out, they said I'm getting 58 joules every second out, which is what a watt means. A 60-watt bulb says you're burning 60 joules every second, but you're not getting it all out. So I just wanted to point out I did not go 58 joules divided by watts. I said, oh, it's 58 joules per second. That's a watt. Why is it smaller number divided by bigger number? Because you can't be more than 100% efficient. And I get 96.7%. Yes? Wait a minute, Mr. Dewick. I thought light bulbs were terribly inefficient. Put your pencils down, I gotta go on a rant. So apparently I already went on my light bulb rant. For those of you at YouTube, I'm not gonna tell my light bulb rant because already went on it. So fine. Fine. D. Manny, what does D want me to find? I don't even feel like it. I don't have any energy. Okay, fine, I guess I will. What kind of energy? Electrical energy. So electrical energy, when we're talking about circuits and power, we said was power times time. That equation is not on your formula sheet, but it's pretty easy to take power equals work over time and say, oh, the work is done by electricity and times the T over. Manny, how much energy are we using here? Sorry, how much power are we using here? Power is measured in watt. How much power are we using here? Because it's a 60-watt bulb. You mean, Mr. Dewick, they actually printed it right on the side of the bulb for me? Yes. You with me, Manny? How long are we leaving the bulb on for? 8 what? Oh, 8 times 3,600. How many joules of energy would this light bulb being left for 8 hours? You get 1728 with 3 zeros. 1728 with 1, 2, 3 zeros, and that's joules. Yes? Travis, what's E want me to find? Well, the cost is going to be the number of kilowatt hours times the rate. The problem is I didn't calculate the energy in kilowatt hours. I calculated the energy in joules. How do I convert this? Well, I'm going to divide by, what was it, 3.6 times 10 to the 6th. I'm not going to make you memorize that conversion factor. If I do give you on your test a question in kilowatt hours, I'll give you that conversion factor somewhere in the question. I won't tell you what to do with it. I won't tell you whether to divide or to times. How many kilowatt hours is 1,728,000 joules? Almost a half a kilowatt hour. Equals 0.48 kilowatt hours. By the way, common mistake, kids think kilowatt hours are power. No, it's power times time. It is energy. It is. So it's going to be 0.48 times, I've scrolled down, Travis, what is the rate per kilowatt hour here? 6 cents? we're too good. We're too good. It's got to stop. Okay. We're too good at generating electricity. To leave a light bulb on costs 3 cents. So what's the incentive to shut the bulb off? The planet. That's my message to you guys today. Once you start paying your own electrical bills, you'll find we do a pretty good job of generating pretty cheap electricity. 3 cents, you might say, I can handle that. But for Pete's sakes, we want to not have to build more dams or coal plants or natural gas plants or any. We want to be able to make do with what we have. We would appreciate electricity a lot more if it was more expensive. I'm not saying I want them to make it more expensive because I use technology and electricity all the time. But it would certainly lead to a pretty dramatic societal change. Power is what over what? Work over time. Electrical power is what? V times I, that's Joule's law. And if you combine that with V equals I times R, Ohm's law, if you give me any two, I can find the fourth. What's your homework? Finish lesson 1 if you haven't already. You guys got a long weekend? And you've conveniently got a short lesson? Holy smokes, you might be able to have no homework for the long weekend. Homework number 1. Number 2. Number 3 is good. Oh, we have to cook hot dogs. Number 7. Oh, this is all review stuff, so I'm going to go back, I think. Sorry, turn back a page, please.
So that's a first.
I think you can also do number 5. And number 4. So I've assigned 1, 2, 3, 4, 5, skip 6, 7. Okay.